Hey everyone, welcome back to another video on numerical integration. We've talked in the past about Euler's method. Euler's method lets you solve for the updated value of a state if you know the previous value and you can calculate the change in the value. Recall that this function f of y and t, this was equal to the differential equation, ddt of y. What we're talking about today, Runge-Kutta methods, we're going to make f of y and t not simply the solution to the differential equation. These methods, f of y and t, these methods will define the function as a weighted average of a series of calculations. Let's say w1, k1, plus w2, k2, plus w3, k3, plus w, so we're using n to iterate over time. Let's use m. Let's say w m and k m. Now, what is the m? M is simply the number of terms in your weighted average. That number, whatever that number is, usually when we talk about Runge-Kutta methods, we will talk about RK, is what they call them. They call them RKs. And then there's a number. Today, for example, we're going to do an RK4, which means that when we do our weighted average, there's going to be 4 terms in our series. RK4s, by the way, they're the standard or the de facto Runge-Kutta that is used to numerically integrate differential equations for various reasons that we'll talk about. So we're gonna look today at Runge-Kutta 4s. Now, what are the W's? W's are weights, and we're going to constrain the weights and say that W1 plus W2 plus W3 plus however many there are, Wm. We're going to constrain all of those weights and say that the sum of those weights are equal to 1. And next, what are the K's? Well, the K's are actually going to be solutions to the differential equations. So we could say K is going to equal f of y and t. Now the y and t, which y and which t? Is it y sub n? Is it the time, tn? What we're actually going to do is we're going to evaluate this the differential equation at a whole series of times. Let's take the bounds, tn, right? Tn, the time associated with yn, and then tn plus 1, the time associated with the update. And we're actually going to evaluate the differential equations at a whole series of times in the, between those bounds, tn to tn plus 1. Okay, let me clean this up and I'm going to list out what the k's are. Here's what the update step for a Runge-Kutta 4 looks like. We're using 4 terms in the series, so W1K1 through W4K4. Here's how we define the K's. Now, I know this looks really busy, okay? Don't panic. All this is we're saying K1 is the function. Remember, the function is the differential equation. So you take the differential equation and you solve it at time and with states. This, the first one, K1, this is effectively Euler's method. Euler's method is a first-order Runge-Kutta method. It's simply the differential equation evaluated at the states. What we'll do next for K2 is we're going to evaluate the differential equation at some small increase in time forward. So alpha, these alpha values then, alphas are bounded between 0 and 1. So if they're bounded between 0 and 1, then that means at most we're taking a single delta t step forward in time. If alpha is 1/2, then we're moving just half time forward. And then instead of using the states, yn, we're actually going to take the k1s and we're going to do a partial update state. So for example, betas are also bounded between 0 and 1. So we're not taking the full K1 and multiplying by the time step. We're just taking a little partial, beta. So we're evaluating the differential equation at a little moment in time forward. with slightly shifted states. Next, we use the calculated K1 and K2, and we can now calculate a new partial update, K3. And K3 is going to, again, we're going to modify the states with K1, and we're going to modify them with K2. Once we have K1, K2, K3, then we calculate K4. You call the differential equation again, you take a step forward in time, and then you have this, again, highly modified set of states. Now, if we want to do all of this, I know this looks really busy, but really it means that we need values for the alphas and the betas. If the value of all the alphas and all the betas are known, then realize this really is as simple as calling the differential equation, getting K1. Next, using K1 and using values of alpha and beta to calculate K2. You use values of alpha, beta, K1, K2, and you calculate K3. You use all of those, you calculate K4. These end up being numbers. You calculate the values K1 through 4, and then you put them back into this equation. So I wrote it this way because we like to see the definitions all on top and then the explanations. When you write your program, you're going to calculate K1, then K2, then K3, then K4, and then you use them, and then you calculate the update. That's the order of operations. So that means we need some values of these constants then, alphas and betas. Well, let's start here. Let's look at first of all, how many variables are there in this description? Well, we have the 4 weights, so I can say W1, 2, 3, and 4. Next, we have alphas. We have alpha 1, alpha 2, alpha 3. Next, we also have betas. So we have beta 1, 2, 3, 4, 5, and 6. So I'm just going to say beta 1 through beta 6. So how many unknowns do we have? Well, there's 6, 7, 8, 9, 10, 11, 12, 13. So in a Runge-Kutta 4 expansion, there are 13 unknowns. And of course, depending on the order of the Runge-Kutta system, if we did RK5, well, then there would be K5, and then we would have another alpha, another W, and 1, 2, 3, 4 more beta values. So the number of unknowns then, it depends on the order of the Runge-Kutta that you choose. Okay. So what can we do to solve for these values then? Clearly, if we want to solve for 13 unknowns, we need 13 equations. Well, you're actually not going to get 13 equations out of this system. We're not going to do the full derivation. You'll get to see that in later classes, but let me just tell you what's going to happen. You can do a Taylor series expansion on this system, and if you do, for a Runge-Kutta 4 model, you get 11 equations. So we have 13 unknowns and we have 11 equations. What does that mean? That means that we actually have 2 free choices in the selection of these variables. You actually get to freely pick 2 of these variables, and then the other 11 then become explicit solutions from the equations. The implication there is that there are in fact infinitely many squared solutions to this set. There's that many valid solutions, which means there's infinitely many Runge-Kutta 4 methods available. So what I'm going to do is I'm going to clean this up, and I'm going to give you the values for these variables for one of the most accepted sets of Runge-Kutta 4s. Recall that Runge-Kutta has infinitely many solutions, so this is a Runge-Kutta formulation. In this Runge-Kutta formulation, look at the weights. The weights are 1, 2, 2, and 1, which means we need to divide by the total, 6, right, to do the weighted average. And then the K values is the function. Again, remember the function is the differential equation. You evaluate the function at the initial states, and then we're going to use the K1 to calculate a new one, K2. We're taking the time step divided by 2, we use the K3, again, time step over 2, and we use K2 to calculate K3, and then for K4, we're taking the full time step, so plus delta t, and we're going to use the K3 to evaluate K4. And we can see in this, this formulation that a lot of the beta values actually ended up going to 0. Okay, so what's the advantage of using this Runge-Kutta over the standard Eulers? Well, you're going to get a much better answer. There will be far less error in your solution using a Runge-Kutta than an Eulers. Now, what if you're using Eulers and you want small error? Well, if you make the delta t go to 0, you make the time step very small, you're going to drive the error to 0 as well. The problem is it's similar to what we saw in, say, Simpson's rule versus rectangular and trapezoidal rule. We know that Simpson's rule was more, it took a bit more coding to do, right? The actual code was a little more complicated, but we actually got significantly less error without having to modify the time step. So the computations are a bit more complex, but we reaped significant benefits computationally by not having to run 10 million cycles, right? As compared to we could run 100 cycles and get similar levels of error. So we have a similar situation between Euler's method and Runge-Kutta's. A Runge-Kutta is more complicated than Euler's method. However, you will get significantly less error. Even though the calculations are a bit more complicated, you do end up saving computational resources at the end. So here is your RK4. You need to, in your current lab, you need to do Euler's method and Runge-Kutta methods. So you have to do, you have to manually program both of these. And you have to do problem 1 is a first order equation, differential equation. Problem 2 is a second order differential equation. Now, I did post a video on higher order differential equations in which we use state variables. So what about doing Runge-Kutta then with higher order differential equations? Well, here is our Runge-Kutta equation. Just imagine that we're using state variables. So with state variables, we recast the system using a vector x. So x n plus 1 is going to equal x n plus delta t over 6. And then this comes right up, k1, 2k2, 2k3, k4. Okay, so the one on top then, this would be higher order Runge-Kutta. And what's the difference? Well, in this first formulation, this first one, say this is for a first order differential equation. So you have just a single differential equation, you calculate a single k1. With the higher order systems, with state variables, these are all now vectors. So x n plus 1, let's say that there are n differential equations, let's say n state variables, n number of state variables. So if you had a 10th order system, you would have 10 state variables. That makes x a vector 10 by 1. So this one is 10 by 1. This, delta t over 6, that's just a number, that's scalar. Therefore, what do we know about these k's? Well, if we're adding these together, they have to be the same size, which means that k1 is a 10 by 1 vector, and k2 is a 10 by 1, 10 by 1, 10 by 1. Or more general, n by 1, right? N by 1. Okay. So if all of these k's are vectors as well, what does that mean down here? Well, when you go to write your code for Runge-Kutta for higher order systems, understand that these k's then are going to be vectors. You're going to do a call on a function that's going to solve you're going to solve the set of first order differential equations, right? And that set of differential equations, you're going to get a set of answers. So it's almost like the k1 will be a vector of k1, and this first k1 is the K1 associated with X1. And the second K1, that's the K1 associated with X2. So you get these Ks for each of the X's. So all of these are vectors. So when you go to code it, if you're having problems, go back and look at how these are coming out and make sure that these are vectors. Okay, this is what you need to know to get the current lab taken care of. I'm going to let you go. Go have a good day. Best of luck.